Unit 9-2, tangents to a circle. We know that a tangent to a circle is a line that lies in the plane of a circle and intersects the circle at one point. The point at which that tangent line intersects the circle is called the point of tangency. So here we have a line that is a tangent to the circle at this point. Theorem 9.1 says a radius drawn to a point of tangency, a radius drawn to a point of tangency is perpendicular to the tangent line at that point of tangency. A radius drawn to a point of tangency is perpendicular to the tangent line. So it hits the tangent at 90, which forms a right angle. And then remember all of that right triangle stuff from chapter 8. If you get a right angle, that means possibly we could create a right triangle. And if we create a right triangle, we have the Pythagorean theorem, the special right triangle rules, the trigonometric ratios. Okay? So a radius drawn to a tangent line is perpendicular to the tangent line at the point of tangency. A radius drawn to a point of tangency is perpendicular to the tangent line. Okay? Tangents to a circle from a point outside are equal. I call this the snow cone effect. We could draw a tangent to the circle and it would hit at this side at a point of tangency. We could draw a tangent to the other side. That theorem says that those two are equal. Segment AE is equal to segment BE. Tangents to a circle from a point outside are equal. Again, I call that the snow cone effect. It just kind of looks like a snow cone. Anyway, so a radius drawn to a point of tangency is perpendicular to the tangent line at that point of tangency. Tangents to a circle from a point outside are equal. Now we can say these in a few seconds and forget them in a few seconds, but we have to remember these forever. So don't forget to study these on purpose so that you remember them long term. A common tangent. A common tangent is a line that is tangent to coplanar circles. A common tangent line is a line that is tangent to two coplanar circles. Common tangent lines could be said to be internally tangent, or they could be said to be externally tangent. So we have a common tangent line. It is a line that is tangent to two coplanar circles. A common internal tangent line is tangent to both circles, but it passes through the segment that joins those centers of the circles. We call that the segment of centers. So a common internal tangent line passes through the segment that joins the centers, which we call the segment of centers. And so this line is tangent to the little circle here, tangent to the big circle here. It passes through the point of the segment that joins the centers. Therefore, it is a common internal tangent line. This is a common tangent line because it is tangent to two coplanar circles. We say that it is a common internal tangent line because it passes through the segment that joins the centers. If you look at the two circles down here at the bottom, the segment of centers is here. There's one line that we could draw that's tangent to both, intersects those both at one point. The point of tangency would be the same point for both circles. That also is a common internal tangent line because it passes through the segment of centers. Okay? Common external tangent lines are lines that are common tangent lines, being a line that is tangent to two coplanar circles, but it does not pass through the segment that joins the centers. So these both have two common external tangent lines intersecting there at exactly one point. Okay? If we look at this example at the bottom, it was kind of hiding. The segment that joins the centers is here. We have a line that intersects both of those at exactly one point. So it is tangent to both of those. They have a common point of tangency. It does not pass through the segment that joins the centers, and so it is a common external tangent line. Okay? And then we could talk about circles being tangent to each other. Circles being tangent to each other. Tangent circles are coplanar circles that are tangent to the same line at the same point. Tangent circles are coplanar circles that are tangent to the same line at the same point. In other words, they have a common point of tangency. And so, like internal and external tangent lines, we also label what we call internal and external tangent circles. If we look at this line that they're both tangent to is here, so they're two coplanar circles tangent to the same line at the same point. They are outside of each other. One is not inside the other one, so we say that they're externally tangent circles. Over here, these are both tangent to the same line at the same point. One of them is inside the other one, and so we say that they are internally tangent circles. Say that circle A is externally tangent to circle B. L is a common internal tangent line because it passes through the segment of centers. Over here we can say that circle E is internally tangent to circle O because one is inside the other. We would say, though, that T is a common external tangent line because it does not pass through the segment that joins the centers. Any questions on tangent lines and tangent circles? Internally, common internal tangent lines, common external tangent lines, externally tangent circles, and internally tangent circles. We also learned that if a radius is drawn to a point of tangency, then it is perpendicular to the tangent line at that point of tangency. And we learned that tangents to a circle from a point outside are equal, and we called that the snow cone effect. We said also when we know that a radius is perpendicular to the tangent line at the point of tangency, we've got to go back and remember all of the Chapter 8 rules about right triangles. Okay. So, daily work, Unit 9-2. It says name common internal and external tangent lines from the following. common internal tangent lines, a tangent to a circle is a line that intersects a circle in exactly one point. A common tangent is a line that is tangent to two coplanar circles. If we look at this diagram, then from A to B, we call the segment of centers. A line is a common tangent line if it intersects two coplanar lines. If it's tangent to two coplanar lines, this green thing, JE, it passes through the segment that joins the centers, and so we can say that JE is a common internal tangent line. And you can name another one. Right here we have C as a point of tangent C, F as a point of tangent C. So line CF is a common tangent line because it is tangent to two coplanar circles. It does not pass through the segment of centers, so we can label it as a common external tangent line, and you could name others. Okay? If we look at number 5, number 5 says name a common internal tangent. To be a common internal tangent line, it would have to pass through the segment that joins the centers. We see nothing that passes through that segment of centers. So in that particular picture, there's not a common internal tangent line. In the next picture, with number 7, there is this passes through the segment of centers, but is it a common tangent line? Well, it's a what to circle H? Well, it hits it in 2 points. It's a secant. You see, it's also a secant to circle G. And so it's not a tangent line to either one. So that blue thing I drew in 7 and 8 is not even a tangent, it's a secant, you see. So don't get to just thinking, oh, if it passes through the segment of centers, it's a common internal tangent. No, it's got to be a common tangent first, okay? A common tangent. What about this right here, AW? Well, AW is a tangent to the little circle. Is it a tangent to the big circle? No. It's a secant to the big circle. AW is not a common tangent line at all. To be a common tangent, it has to be tangent to two coplanar circles. That was only tangent to one of them. Okay? Well, what about EF? EF is tangent to circle H at point E, and it's tangent to circle G at point E. It is tangent to both, so it is a common tangent line. It does not pass through the segment of centers, so it is an external, a common external tangent line. So EF is a common external tangent line. The thing that passed through the segment of centers was not a tangent, it was a secant, so this one does not have a common internal tangent line. Okay? All right. Let me do a little bit of erasing. So the first thing when you talk about common tangents, you got to make sure it's a tangent to start with. A tangent intersects a circle in exactly one point. It's a line that lies in the plane of a circle and intersects a circle in one point. A common tangent line is a line that is tangent to two coplanar circles. A common internal tangent line is a common tangent line that passes through the segment of centers. A common external tangent line is a common tangent line that does not pass through the segment that joins the centers. It says name a pair of internally tangent circles. This last set are internally tangent. The reason they are, to be tangent circles, they have to be tangent to the same line at the same point. Circle G and circle H were both tangent to line EF at point E. So that makes them common tangent circles. One of them is inside the other one. The fact that one is inside the other one is what makes them common internal tangent circles. So our common internal tangent circles are circle G and circle H. Any questions on that? Okay, find the missing links and the angle measures. Find the missing links and angle measures. I'm going to slide that up just a little bit more, and I'm going to white out the bottom so we can have some room to work. It says BC is tangent to circle A. Well, if BC is tangent to circle A, C is our point of tangency, A is the center. If a radius is drawn to a tangent, then it is perpendicular to the tangent line at the point of tangency. So the radius drawn to the point of tangency is perpendicular to the tangent line. I say it backwards every other time. I'm sorry about that. But look what that creates for us. That creates for us a right triangle. In a right triangle, a squared plus b squared equals c squared. It says angle ACB. Angle ACB is that 90-degree angle. If we had to have a reason, we would say radius drawn to the tangent line is perpendicular to the tangent line at the point of tangency. Segment AB. To find AB, it is the side opposite the right angle, so it's the hypotenuse C. And so we're going to use C squared equal A squared plus B squared to solve. So we take the hypotenuse C squared equal one of the legs 5 squared plus the other leg 12 squared. We're going to do the exponents. C squared equal 25 plus 144. We're going to do the addition. C squared equal 169. We've done all we can do to simplify. We're going to undo the square with the square root, and we get C equal 13. And now we want angle B. Well, how do you find angle B? We only know one angle. You can't add 2 up and subtract from 180. What are you going to use? You're going to have to use a trigonometric ratio, right? Angle B. So we want to find angle B. That's the angle we're looking for. We write down the angle first, and then we look at the sides and see how they're related to the angle to find the function. We're either going to use sine, cosine, or tangent. The sides that we know are the 5 and the 12. They're both legs. The 5 is the leg opposite angle B. The 12 is one of the sides of angle B. We call the sides adjacent. And so that's leg adjacent. We have leg opposite, leg adjacent. The function that's leg opposite, leg adjacent, the tangent ratio. So leg opposite, leg adjacent is tangent. And then we have to set up our fraction. Tangent says you put leg opposite. On top, it was 5. leg adjacent on bottom, it was 12. And so we have our ratios set up. It's order of operations time. We're going to do what we can to simplify, so we do that division. So we would have tangent angle B is equal to, we're going to do 5 divide 12 and take it out 4 decimal places. We're going to first go to mode and double check that it's in degrees. Second quit. We'll clear that out. 7/12, I think I forgot. It's 5/12. Yes, I knew that. Here we are. Lost my calculator. So we're going to have 5 divide 12. We take it out 4 decimal places, 0.4167 rounded. Now I'm going to go ahead and show you how to make it round, since we've not let you for a long time and we're about done. So now you know how to round. So we're going to go to mode. The second thing there is float. So we're going to arrow down to float, and we're going to go out to 4. And what that'll do, we hit enters, make it round to 4 decimal places. Okay, so watch this. Now we're going to do that again. 5 divide 12, enter, and then it rounds it for us to 4 decimal places. Okay, I wanted you to have to know how to round before we start using the calculator to round, so I waited this long. 0.4167. We've done all we can do to simplify. Now we're going to undo. We're going to undo the tangent function with its inverse function, inverse tangent. The inverse tangent function cancels the tangent function. And so we get angle B is equal to inverse tangent 0.4167. Stepped on a book. That's why I did that. Sorry. I like to trip. So we're going to go back to the calculator. Second tangent, inverse tangent, 0.4167, close, enter, 22.62 degrees rounded, 22.62 degrees. Okay? So we begin all of that with a radius drawn to a point of tangency. We said if the radius is drawn to the point of tangency, then it's perpendicular to the tangent line at the point of tangency. Therefore, that angle was 90. Therefore, we had a right triangle. Therefore, we could apply the Pythagorean theorem. And we could apply the trigonometric ratios. And we can do our right triangle solving stuff from chapter 8. Okay. Now let's look at this problem over here. It says FZ is tangent to circle X and circle Y. See what that does for us. I'm going to do some more whitening out in case I need this space for this problem. So just going to wipe all that out. Go ahead and get this out of our way. That way we can just kind of focus on that. Probably a little more house cleaning than we needed, but anyway. So what we have is X drawn to F. That's a radius drawn to a point of tangency, so it's perpendicular. So that's a right angle. A radius drawn to a point of tangency is perpendicular to the tangent line at that point of tangency. Same thing over here. YZ is a radius drawn to a point of tangency. Therefore, it's perpendicular to the tangent line at the point of tangency. Therefore, that's a right angle. So those angles are equal because they're both right angles. The two angles at E are equal to each other because they're vertical. All of a sudden, we have two angles of one triangle equal two angles of another. Therefore, those triangles are similar by angle similarity. That takes us back to chapter 7. We're going to name that similarity X. Well, first of all, let's name the angles. Angle XFE was 90 because the radius is perpendicular to the tangent line of the point of tangency. YZF is 90 for the same reason. Our F and our Z were 90. F is in the middle, so I'm going to go ahead and put Z in the middle. I'm going to go ahead and name what we already knew, that F and Z were equal because they were 90. The E's were the verticals, and E was last here, and so E goes last here, so we already knew that. Well, the only thing left in the second one is Y, so the Y must be equal to X. A little bit easier to match it up there when you go ahead and match up what you already know. Now, if that's true, that they're similar, then that means that the sides are in proportion, right? Similar figures are the same shape. In similar figures, corresponding angles are equal, and corresponding sides are in proportion. So we have Fx is 6. We have Fe is 8. We have Yz is 3. And we want to find Ze. So we can set up a proportion 6 over 3, that pair of corresponding sides, is equal to 8 over EZ, that pair of corresponding sides. You may say, well, I can see how Fx goes to Yz, but I can't see how Fe goes to Ez. If you can't flip that around in your head, then just look at this. Fe is the last two letters. Ez is the last two letters. Fe has to go to Ez. Last two letters go to last two letters. So we have a proportion. We could reduce the 6 over 3 to 2 over 1, but we're going to leave it. 6 Ez is equal to 3 times 8 is 24. We're then going to undo multiplication by division, and we get Ez is equal to 4. So we had two radii drawn to points of tangency, so we got two right angles. We had vertical angles are equal, so we got similar triangles by angle similarity. If the triangles are similar, then the sides are in proportion, so we could set up a proportion with two pairs of corresponding sides and solve for the value of Ez. Any questions on that? So everything we've learned in the geometry book is cumulative. We have to keep remembering those things and be able to use them as we continue. All right. And what we've got going on number 20 is two things. We've got tangents to a circle from a point outside are equal, and we have transitive property. We know that if this is 24, then this is 24 because those are both tangents to this circle right here. And tangents to a circle from a point outside are equal. Kind of call that the snow cone effect. Well, the same thing here. This is also 24 because those are both tangents, and tangents to a circle from a point outside are equal. And if that's 24, then this is 24 because we've got two tangents to this circle, and tangents to a circle from a point outside are equal. So we got 24 equal 24 equal 24 equal 24. Looks a little bit like a transitive property thing going on. But anyway, if this equal this, and this equal this, and this equal this, and that equal that by transitive, you see. Okay? All right. When you solve these things, there's all kinds of things that can happen. Uh, you may or may not need this. I didn't even read this close, to be honest with you, but we could draw that, and it would be 90 there. We could draw, oh, that was weird. We could draw this, and it would be 90 here. We could draw this, radius perpendicular would be 90 there. I'm sure not getting very straight lines. 90 out of that. We could draw the segment of centers. Look at what all you got going. You got a pair of congruent triangles here and here. Another pair of congruent triangles here and here. You got one of the little red ones is similar to one of the little green ones. So you got similar triangles going on. You got two pairs of congruent triangles going on. You got all kinds of stuff going on there. So you got a lot in the geometry book to bring to mind as you do number 21. Okay? We'll let you dig on that one. And so that's the end of daily work 9-2.